Hey everyone, and welcome. Today we're going to crack the code on a really fundamental programming puzzle. We're going to teach a computer how to draw, not with any fancy graphics, but with the pure, simple logic of loops.
So, here's the big question, right? A computer is pretty literal. It just follows instructions one by one, in a straight line. So how in the world do we get it to create something complex, something structured, like a shape? Well, the answer isn't a ton of complicated code. It's actually one simple but incredibly powerful idea.
So let's start with a little puzzle. Your task is to draw a 4x4 square of stars. Now, you could just type out 4 lines of 4 stars, but that's kind of cheating. We need a generic solution, a blueprint, that works whether we want a 3x3, a 5x5, or even a 100x100 square. We're looking for the recipe, not just the finished meal.
Okay, let's dive into this, because this is the key that unlocks pretty much all pattern-based problems. The secret is something I call the two-loop blueprint. And the easiest way to picture it, think of an old-school typewriter. You've really only got 2 main actions: moving to a new line and then typing characters on that line.
First up, you've got the outer loop. Think of this as the big carriage return lever on that typewriter. Its one and only job is to say, all right, this line is done, let's slam this thing over and move down to start the next one. You need 4 rows, this loop runs 4 times. That's it. Simple.
And this is where that brilliant idea of nesting comes in. See, for every one time that outer loop runs, we execute this inner loop completely. This is the part that does the actual work. It's like typing the characters on the current line. It's a little sub-process that says, okay, on this new line the outer loop just gave us, here's what you need to print.
So the whole thing becomes this simple 2-step dance. The outer loop moves to a new line. Then the inner loop fires up and prints everything needed for that line. Then the outer loop moves to the next new line, and the inner loop runs all over again. New line, print. New line, print. Okay, enough theory. Let's see this thing in action.
All right, let's move to our first test case and see how this actually builds our square. We're going to apply our brand new blueprint to create that perfect 4x4 grid of stars.
So here's the crucial part, how these two loops talk to each other. For our 4x4 square, the outer loop is going to run 4 times, right? 1 for each row. And for each of those 4 runs, the inner loop also runs 4 times, printing 1 star each time. So you get 4 new lines with 4 stars printed on each. And just like that, you have a perfect square.
That was easy enough, wasn't it? But you know, perfect squares are a little boring. What happens when the shape isn't a perfect grid? What if the number of characters we need to print changes on every single line? Well, this is where our simple blueprint needs to get a little bit smarter.
Let's tackle a triangle. Now, this shape is the perfect next step. It looks simple, but it's the thing that's going to force us to evolve our blueprint from a rigid, fixed set of instructions into something way more dynamic.
And here is the absolute core difference. With the square, the inner loop was predictable. It always ran 4 times, no matter what. But for a triangle, Row 1 needs 1 star, row 2 needs 2 stars, row 3 needs 3, and so on. A fixed inner loop just isn't going to cut it anymore.
The solution, though, is so elegant. It's beautiful. We don't need a whole new blueprint. We just need to create a connection, a little conversation between our 2 loops. We're basically going to tell the inner loop, hey, before you run, just do me a favor and check which row number the outer loop is currently on.
And just look at the result. If the outer loop says, hey, I'm on row 1, the inner loop goes, got it, I'll run just 1 time. If the outer loop is on row 2, the inner loop runs 2 times. We've made our blueprint intelligent. The number of stars it prints is now directly tied to whatever the current row number is. Pretty cool, huh?
All right, you ready? For our final challenge, we're going to build a pyramid. This is going to combine everything we've learned so far: managing rows, dynamic characters, and it's going to add one final, really interesting layer of complexity.
Now, when you first look at a pyramid pattern, it seems way more complicated. But the trick, as always, is to just break it down. Instead of thinking of one inner loop trying to do everything, you have to realize that for each line, the computer is actually doing 3 totally separate jobs, one right after the other.
Here's how it works. For each new line that the outer loop gives us, we just run a sequence of inner loops. First, a loop runs to print the blank spaces on the left to get the alignment right. Once that's done, a second loop kicks in and prints the increasing numbers. And finally, a third loop prints the decreasing numbers. That's it. A visually complex shape just becomes a simple, linear set of instructions.
So, we've drawn squares, triangles, pyramids. Great. But so what? Why does any of this actually matter? I mean, the goal here was never just about making stars and numbers appear on a screen. It's about building a core programming skill that you'll use forever.
What you're really learning here is how to think like a programmer. You're learning to take a big, intimidating problem and break it down into small, manageable, repeatable steps. You are building the mental muscle for logical problem solving that applies to absolutely everything else in software development.
And you know, this quote just nails it. Shraddha Kapra from Apna College said this, and it's perfect. To be able to write loops easily and quickly later on, today we must sit down and dedicatedly practice writing loops in this chapter. This is it. The practice you do on these simple patterns is the foundation that lets you tackle much harder problems later with speed and with confidence. This is where you build fluency.
So that leaves us with a final thought to chew on. We use this logic to draw shapes. But what other seemingly impossible problems in data processing, in automation, even in science, can be solved by just finding the outer loop and the inner loop, by breaking them all down into simple, elegant, repeating steps? Thanks for watching.